So the next section we are going to work with is 3.4. And in 3.4, we're going to talk about measures of position and outliers. So we're going to work with z-scores, percentiles, how we're going to get those percentiles and then interpret them. I'll talk more specifically about quartiles, interquartile range, and then determine how we find outliers. All right, so to get started, we are going to talk about what a z-score is. So a z-score represents the distance that a data value is from the mean in terms of the number of standard deviations. We find it by subtracting the mean from the data value and then dividing this result by the standard deviation. There is both a population z-score and a sample z-score. The formula is the same as far as that it is always data minus mean divided by the standard deviation. The only difference is the population mean and standard deviation symbol versus the sample mean and standard deviation symbol. Okay, so this is why we talk about standard deviations and means already. So this allows us to compare two data sets together. Two different data sets, male and female, let's say, will have different means and standard deviations. So we may not be able to very easily just compare two values to see which is actually better for their gender. So it allows us to compare across data sets. It allows us to compare with different means, standard deviations, to see who is better overall. Okay, a z-score has no unit. The value of 0 represents the mean, and we are going to go basic by standard deviations. The first standard deviation is 1, the second standard deviation is 2, the third standard deviation is 3. All right, so example of where we would use this. Determine whether the Boston Red Sox or the Los Angeles Dodgers had a relatively better run-producing season. The Red Sox scored 876 runs and play in the American League, where the mean number of runs scored was 731.2, with a standard deviation of 72.6. The Dodgers scored 804 runs and play in the National League, where the mean number of runs was lower at 710.8 with a standard deviation of 60.2 runs. So because they are in different leagues, I cannot just compare them because they have a different overall mean and standard deviation for their group. So what I'm going to do is I'm going to put all the Red Sox data together. Here is their data value, their mean, and standard deviation. And then in another color, the Dodgers, their data value, their mean, and their standard deviation. Okay, what you are going to do is then conduct the equation back here of taking your data value minus your mean and dividing that result by the standard deviation. So I'm going to do that on the next slide here. So 867 is the data value. Minus the mean, 731.2. Take that result and divide by 726. That gives me a value of 1.99. So I am just shy of 2 standard deviations above the mean. I will do the same with the Dodgers. Their data value is 804. Subtract their group's mean and take that result divided by their group's standard deviation, and I get 1.55. So for this, I am wanting the higher run values. So the one that did better were the Red Sox. They had a run production of 1.99 standard deviations above the mean, while the Dodgers were at 1.55 standard deviations above the mean. So the Red Sox had a relatively better year at scoring runs than the Dodgers. The mean upper arm length of a 19-year-old male is 38.6 centimeters with a standard deviation of 2.9 centimeters. Okay, so we got male. has a mean 38.6 and a standard deviation of 2.9 versus the females over here have a mean of 35.8 centimeters and a standard deviation of 2.8. Who has the relatively longer upper arm? A male with a value of 41.1 or the female with a value of 38.4. Again, we're doing relative because it is based specifically on their gender and how they compare to the remaining in their gender. Okay, so we are going to take our data value. Let's start with the males here. 41.1, subtract the mean, and divide that result by the standard deviation. Okay, you must be careful to do this in 2 steps. So you must first take 41.1 minus 38.6 and get that answer. That answer is 2.5. If I divide that by 2.9, my z-score is 0.86. We're going to repeat this with the female data. So theirs was 38.4 minus their mean of 35.8 divided by their standard deviation, 2.8. So again, I'm going to take 38.4 minus 35.8. The entire top has to be calculated first. Okay. And then I take that result divided by my standard deviation. And this one gives me 0.928. So it's going to round to 0.93. Okay. So the male value was 0.86 standard deviations above the mean, where the female value was 0.93 standard deviations above the mean. So who's further above the mean? Well, that would be the female. So the female has a relatively longer arm, upper arm, in this situation. Now, one thing I'd like to note, if you are running a race, you are better if you are faster than your competition, which means your time is below average. You want your time to be smaller or less than average. So what's going to happen there is you're going to get z-scores that are negative. It is possible to get negative z-scores. Negative z-scores just mean that your value is below the mean. And in a case of running a race, you want to be further below the average pace. You want to be running faster. You want your time to be less than the average runner. So in a case like that, you're going to want the larger negative number. So there are times where you will be working with negatives and you may have to determine, hey, do I want that negative number? Do I not want that negative number? Okay, so just make sure you're looking at the situation to know, hey, do I want the highest number or do I actually want the smallest number? Okay. All right, so the next thing we talk about here is percentiles. The kth percentile notated PK of a data set basically is just telling me what percent happens below that value. The most common examples for these are when you were younger or if you have children that take state testing, and it will tell you your child scored in the 62nd percent. What that means is they scored above 62 people, 62% of people. So 62% score below what they got, and then 38% scored above what they got. Okay, you also see this in measurements when you have a child and you go and you do height, weight, and head circumference. And they're going to tell you, oh, your child is in the 50th percentile for weight, or the 75th percentile for height. What they're doing is they're telling you how your child compares to other children at that specific point in time. Okay, so anytime I give you a percentile value, if I tell you it is the 68%, that means 68% are below you and 32% are above. So the value they give you is how many are below you. So what does this mean in a practical explanation? So Jennifer just received the results of her SAT exam. Her SAT mathematics score of 600 is in the 74th percentile. So what does that mean? Well, that means 74% score below 600 in math on the SAT. Or I could say the opposite. 26% score above 600 in math on the SAT. Which I'm pretty sure is what is written on the next slide here. I forgot the slide was there, so I wrote it out for you. Same thing here. 74% of SAT math scores are less than or equal to 600. And 26% of them are bigger. Okay, so there were 26% of the students that did better than Jennifer. Usually, if we talk about these other percentiles, we're talking about very, very large data sets. It doesn't make any sense to talk about percentile values if I only have, like 25 pieces of data or anything under 100. Really, it doesn't make any sense to kind of talk about those percentiles. So really, these are for very, very large sets of data. There are tons and tons of people that take the SAT every year. So that's where this makes sense. Okay, so another one here. The graduate record exam, the GRE, is a test required for admission to many U.S. graduate schools. The University of Pittsburgh Graduate School of Public Health requires a GRE score no less than the 70th percentile for admission to their Human Genetics MPH or MS program. What does this mean? Okay, so they require no less than the 70th percentile. So 70% will score too low and cannot be accepted. So only 30% of people that take a GRE would be allowed to go into this program. So 30% will score above and can be admitted. Okay, the main percents we're going to work with here are quartiles, though. Quartiles are quarters. They're going to divide our data into fourths, or 4 equal parts of 25% of data. So the first quartile, Q1, is the bottom 25% of data. So therefore, that value is the 25th percentile. The second quartile is going to be the 50% mark. That is also called our median. The next one is called Q3, the third quartile. And up to that point is now 75%. So I've broken it into quarters. So quarter 1, 25, quarter 2, 50%, quarter 3 is the 75%, and then the end values are our smallest and largest values, or our max and min. Okay, so how are we going to do this? Again, as always, I will start by showing you by hand how you could do this, and then I will show you in StatCrunch how we could also get these results. So the first thing you have to do is you are going to arrange your data in ascending order so that we can get the median. Okay, so we've already figured out how to find the median. Then what we're going to do is we're going to find the median of the bottom half and the median of the upper half. And now it's going to give me Q1 and Q3 respectively. All right, so the Highway Loss Data Institute routinely collects data on collision coverage claims. Collision coverage insures against physical damage to an insured's individual vehicle. Data below is a random sample of 18 collision coverage claims based on data obtained from the Highway Loss Data Institute. We're going to find the first, second, and third quartiles for this data. Okay, so before we can do anything, we are going to have to put our data in order. So there are 18 observations. So the median is going to be the average of the 9th and 10th. So put them in order. Here they are all in order. So I've got the first 9 and then the last 9. So the median is going to be the average between these two values. If I add 1,657 to 1,953, the median is 1,805. So the median is actually right in the middle there. Once I have found my median, I can then find my Q1 and Q3. So working with this lower set of data here, cross off 2, cross off 3, cross off 4. Here is quartile 1 value. So median we calculated was 1805. And we're gonna do the same thing with the second 9. Here is Q3. And it explains that on the next slide here of how they did it, working their way into the middle. Okay, so what do these values mean? Well, if Q1 is 25%, 25% of our collision claims are going to be less than that first quartile value of 735. 75% are going to be greater than that. Okay, our median was 1805. So 50% are going to be lower than that. 50% are going to be greater than that value. Our Q3 value was 4,668. So that is 75%. So 75% are going to be lower than that value. 25% are going to be higher than that value. So how would we do this in StatCrunch? All right, well, let me show you. Okay, still got my StatCrunch page here. I think I still have that data. I still have that data set here. So my employees data set is right here, those 7 employees. That's that same 7 employees. Find and interpret the quartiles. So remember that this was the distance in minutes it took to get to work for these individuals. So we are going to go to that same place we've been going for chapter 3, summary stats on the column for my employees, and I'm going to click compute. Sorry, this is not large enough here. It is going to give me those values, Q1, median, and Q3. So 25% of people take 18 minutes or less to get to work. 75% take more than those 18 minutes to get to work. The median is 25 minutes. So half the people take less than 23 minutes to get to work. Half the people, it takes longer than 23 minutes to get to work. And then Q3 here is 36. So 75% of people, 36 minutes or less to drive to work. And the remaining 25% of employees, it takes more than 36 minutes to get there. Again, all of this stuff's really just going to be in here with StatCrunch. You don't have to calculate them by hand. It's definitely going to be a lot easier if you're working with a large data set to be able to pull those values up. So I'm just gonna grab a quick data set here. This is miles per gallon that you get in a smart car. So if I wanted to find my quartiles again, I just go to summary stats on my columns. I click it and it's going to give me my Q1, my median, and my Q3. So 25% score below this, 75% or above. This is my 50 value. So half are below this, half are above. And my Q3, 75% or below, 25% are above. It's all there. It's all going to be there. It's just a matter of then, can you interpret the results? So again, focusing on the interpretation, the understanding of what it is you're calculating, not just, hey, can I calculate it? Last thing we can talk about in this section then, I get back to my PowerPoint here, is the interquartile range. The interquartile range is the middle 50% of observation. So it's between that 25 and 75% value. So very easily take Q3 minus Q1, and that's going to give you your IQR. So if I were to use that collision claims data, my Q1 was 735. My Q3 was 4,668. So I could subtract those two values and find there's a difference of $3,933. So the range, the spread of the middle 50% is 3,955. Okay, so regular range was min to max. The entire data set, how far does this spread? Interquartile range is 25 up to 75%. So this is the middle 50%, or where we're expecting kind of the more average values to fall. Okay. Again, in IQR, if it is a larger value, just like a regular range, the larger it is, the more spread apart your data is going to be. I could easily go back to any of my data value sets that I did back here. So smart car, just to look here. So I think I can type right here. So my overall range, it tells me, is 16. If I want to find my interquartile range, plus the 25, the Q1 to Q3, I would take 41 minus 36.85. And if I do that here, 41 minus 36.85, we get an interquartile range of 4.15. Okay. So why do we have these values? Well, we have the interquartile range because that tells me if I have outliers. If we have a symmetric set of data, we're always going to talk about the mean, and we're going to talk about the standard deviation. Remember that if our data is skewed one way or the other, the best result to talk about is the median. And then we're also going to, in this case, use the interquartile range. So anytime we have skewed data, you're going to more likely talk about the median and the interquartile range, because when data is skewed, we've got those really far values, those outliers that would pull my mean up or down. Okay, we've got some outliers, some value that is too far out of the rest of the data. So remembering that mean and standard deviation are not resistant. The median is much more resistant. It is not impacted by those large values or really, really small values. Can go both ways. The last thing we're going to talk about here is these outliers. And these outliers, we're really going to talk about more when we create a graphic in the next section here. I'm just going to discuss it here quick, and then we'll hit it a little bit more in the next section. How do you check for outliers? So outliers are data values that are more, they're extreme values. They are far away from the rest of the data set, and there is a mathematical equation to calculate that. So in order to do that, you need the first and third quartiles, and you also need the interquartile range. What you're going to do is you're going to calculate these two things called the lower fence and the upper fence. The lower fence takes the Q1 minus 1.5 times the interquartile range. And the upper fence takes Q3 plus 1.5 times the interquartile range. If any value is below this lower fence, it is an outlier. If any value is above this upper fence, it is also considered an outlier. So we're going to use that same data set we've been working with, where we had Q1 was 735, Q3 had 4668.
The interquartile range is 3,933. So then we can use our calculations to find the lower fence, which takes the Q1, 735, minus 1.5 times interquartile range of 3,933. You're going to want to type it exactly as you see it in a calculator, and you're going to get negative $5,164.50.
I can't spend negative money. So clearly that value, anything I find on the low end is going to be within my data set here. The upper side would take my Q3, 4668, and 1.5 times interquartile range. And I would get $10,567.50. So what I would do is I would have to go back and look at the original data set back here. And I see that this value is really, really high. This value is outside of the scope of my model. This value is an outlier because it is well above the upper fence that I calculated of $10,567.50. And those calculations are here on the last slide as well. There are no observations below the lower fence. However, there is an observation above the upper fence, and that 21,147 is going to be an outlier. Okay, so like I said, we will work with this again in the next section here when we create a visual representation of this, and you'll work with them a little more in your practice. But I will see you in the next video.